Hello everybody, my name is Alex Matassa, and today I'll be presenting Extreme View Synthesis by Choi et al. So an outline of my presentation, I'll start with an introduction, then I'll cover two related works, then I'll give an overview of the solution that they propose, then I'll go in detail how they synthesize novel views, and then I'll cover how they refine these synthesized images. Finally, I'll do some evaluation and results, and I'll follow up with a conclusion. So what is novel view synthesis? Novel view synthesis is capturing visual content from various camera points of view to render a new perspective. This enables telepresence applications. One common example is Google Maps, the use of 3D imagery within a 2D pane and being able to navigate through that scene. This is very commonly used in all of virtual and mixed reality solutions. So the first paper is stereo magnification, learning view synthesis using multiplane images. The ideas presented in this paper aren't used too much throughout the paper, but the results are used for evaluation of the proposed solution. So a brief overview of the solution is they give a reference source image with the pose provided. Then they take a second source image, which is a similar viewpoint, and they do a plane sweep of this image to get various information throughout the different depths of the image. This is fed into a neural network, which extracts a background color image and blending weights. These blending weights are used to create different representations of the image at different depth values. These different blending weights and background colors are blended to create an MPI representation. MPI stands for a multiplane image. And I'll go over what an MPI image does for the actual synthesis in the next slide. But essentially, with the use of a colored image and these alpha images, they're able to synthesize new images. So a multiplane image is an RGBA version of the image at different depth levels or disparity levels. Disparity is commonly used in these papers to describe the inverse of depth. So as something has a farther depth, it'll have a smaller disparity, and if something is a shallower depth, it'll have a larger disparity. These planes describe fronto-parallel scenes, so essentially the same scene with being parallel at different depths. The novel view synthesis is created using these RGBA images and basic camera parameters, allowing for a homography-based novel viewpoint. They allow for novel viewpoints to be created through homography-based calculations, along with alpha compositing, which allows the objects within the images to have a certain value, allowing for closer images to have a larger alpha value and farther images to have a lesser alpha value. The next related work that's more important to this paper is the DeepMVS architecture from DeepMVS Learning Multiview Stereopsis by Huang et al. This network is a three-part process. The first part is a patch matching network that finds similarities within different images. These images are all of the same objects but from different viewpoints. The next part is an intra-volume aggregation, which takes the features from these different patches and aggregates them into one common feature map. From there, the features can then be aggregated into a single volume aggregation, which gives a total summary of the image depths and within the input image. The output is a disparity map, which is just a map that describes the different depths within the image. I'll cover this network within all three parts. I'll cover it in detail because really all parts are utilized within the paper I'm presenting. So the first part is patch matching. What patch matching is it takes a reference image along with single patches from a plane sweep volume and the camera pose of those images. The camera poses can be given manually, or they can be defined using a structure from motion algorithm in column map. This patch matching algorithm extracts a 64-channel feature from both patches and then concatenates the two patches into a single feature of a 4-channel patch. This process is repeated for all the images at all the different depth levels. In this specific paper, they use 100 depth levels. That seems to be the standard between all these view synthesis papers. They all happen to use 100 depth, and the reason being is it's kind of the middle ground for memory consumption and speed. So the next part of the network is the intra-volume feature aggregation. This is a UNet architecture that also encodes values or encodes features from a VGG-based network. What it does is it takes neighboring images and concatenates the 4-channel patches that were taken from the previous network. While decoding and then encoding, the features from a VGG base, as shown down here, are encoded at every level of the encoding process. They're just concatenated on, and then once the image or the channels are then decoded, you're outputted an 800 channel volume, which essentially just describes the disparity within the whole image. So finally, now that we have a volume representation of all these different scenes, we can then aggregate all the scenes into one scene. And this is done by using max pooling. The reason max pooling is used is because it allows for the network to have an arbitrary amount of images as well as an arbitrary image order. The reason being is we only care about the important features within this disparity map, so we just look for the maximum values. And then finally, once these values are aggregated, we downsample using standard convolutional layers, and you get a D-channel pixel map, which, as stated, is 100 channels in this example. So a little example of the disparity map. Given this input, we then calculate the pose using a standard structure from motion algorithm. These plane sweep volumes are then inserted into the DeepMVS, and you're outputted a disparity map like this, where the darker colors represent farther depths or closer disparities, and the closer images represent, or the closer objects represent a smaller disparity, or larger disparity, sorry. And as you can see with these examples here, for this staircase, you can clearly see as the depth changes within the stairs, the same is present within this, and with all these images. This can be applied to any real-world images. So what is trying to be solved from this paper? View synthesis is not a new topic. It's been around for decades, but they want to propose a solution that allows for extreme views. And extreme views is defined as having a small number of input sources, as little as 2 in this network. And they want to be able to synthesize new views that are varying substantially from the original viewpoints. In addition, they want to be able to generate synthesized images that create disocclusions by viewing certain objects from different viewpoints. And finally, they want to be able to increase the baseline magnification of these images, allowing for more clear images. So the proposed solution is to estimate depth probability volumes using the DeepMVS network. These depth probability volumes are just the disparity maps. They just rename it in their paper. Once they have these depth probability volumes of all the source images, they can then fuse them and then warp them in relation to the novel view depth. This is done with a simple affine transformation. Once the synthesized image is created, there will be artifacts and holes within the image, just as expected when you have a new novel viewpoint. So what they do is they propose a refinement network that takes this image and clears it up at a patch level. So an overview of the whole architecture. First, we start with these images and their poses, as described with the DeepMVS architecture. This multi-view depth estimation is just the DeepMVS network. So they run each of the images through the DeepMVS network and are outputted a disparity map for each of the different images. This can be n number of samples, but obviously for extreme cases, they want to keep the number as low as possible. So once they have all these disparity maps, they're then fused together, and a warping is applied based on the virtual camera position. These values and transformations are just are homography-based transformations. Once the novel viewpoint is warped and fused together, we then have a depth map that accurately describes the new novel point of view. From there, we can synthesize the new image using a pixel-based algorithm that just simply goes pixel by pixel and based on the depth map creates the image. From there, they then refined the images using candidate patches from the original source images. I'll fully describe how they actually choose patches later on. And once that is done, they now have a clear image, which results in up to 30 times magnification and clear viewpoints that are novel. So how exactly do they estimate the depth probability volume? Well, the way DeepMVS works is by treating depth estimation as a classification problem, similar to image classification. There are n depths, which in this case is 100 classes, so one value for each depth. They define a probability distribution for each ray pointing from the source camera to the pixel within the image. And the collection of all these rays probabilities is denoted as the depth probability volume, or d sub I. To train this network, they just use a cross-entropy loss using a ground truth one-hot vector. And what this means is, for a given pixel, if there are 100 depth values, let's say the depth is 20, then the value at 20 will be 1, and the rest of the values will be 0. So the problem with estimating depth probability is it works fine when you have objects that are in clear, obvious positions, but for edges, it can be difficult to tell what is in the foreground and what is in the background. So as you can see for this building in the background, the estimated depth is around 15, 16, and for the tree, the estimated depth is around 40. But for the corner of the tree, the network struggles at detecting is that in the foreground or in the background. So what happens is you end up getting a multimodal distribution where the network isn't sure. It knows it's either one of these two values, but it's not clear at which one it is. So in order to estimate the depth probability of the novel view, there's two solutions. The first being the simple one, which is averaging the intersecting rays from the source cameras. This is computationally expensive and very slow, and this network is already slow to begin with, so they needed to speed it up a bit. So the faster solution is to resample all the depth probability volumes with respect to the new novel view. And they do this by using what's called a nearest neighbor sampling. They don't really explain exactly what this means, but based on my understanding and reading through the paper, it basically means they look for objects that are similar within the different depth maps and assume that if an object is there, they just give it a value of 1. And the objects are then summarized and you create a new novel view that has different values, 0 through whatever. This is then normalized and you create the final viewpoint. So as you can see, here is the first disparity map that's given. The purple represents an object. So these values would be set to 1, and all these other values of the grid would just be set to 0. Then in relation to the new novel viewpoint, they warp these pixels and accumulate them, averaging a 1 value for all these. As you can see, they then extend these values all the way to the farthest background depth. Not too sure why they do that. They don't explain why they have two versions of the novel viewpoint here, but that's the case. And then once they have the first disparity map compared to the new novel viewpoint, they can apply that to every other disparity map, which is shown with this D sub 2 and these green objects. So where these overlap, in this scenario, you would have values of 2 here, meaning that there's very clearly an object here based on the 2 disparity maps, and we know for sure that something is there. So once we have the final disparity map of the novel view, you can then synthesize the actual image. This is done pixel independently from back to front. The reason they do from back to front is because they want to synthesize these objects as they come. So with an object in the background, it might seem fine for one disparity map, but as other disparity maps give information that shows maybe there's an object closer, we want to override that pixel. So that's what this 1 indicates. It's an indicator function that takes the disparity map of the novel view and looks at that specific depth. And if there's an object there, we look at, is that object in the background compared to the new object that's in that place, or is it in the foreground? If the object's in the foreground, then we don't care and we just set it to 0. If the object is in front of the old object, then we care about that pixel. So we replace that with a 1. That value is just multiplied by the pixel at that original source image and then is weighted using this R function. They don't really describe how they get the R function, but they say it's a weighting function based on the camera parameters and the principal axis from the source image and the novel viewpoint image. So here's an example of view synthesis. So in the bottom area, you can see 4 different cameras, 2 gray cameras, and then a green and a red. The gray cameras are going to represent the source images, and the green and the red cameras are going to represent the synthesized images. So for this gray camera, here's the scene. Then for this gray camera, here's the scene. And then for the green camera, you can see we now have objects in the right side are more present, like this animal in the right corner, this pole, and things like this pole and this tree are now pushed out farther back and not as important to this viewpoint. However, if we go to the red camera, we can now see that objects on this side are much more clear and in the foreground. In addition, you can also see that the animal that was once in the right side is no longer here because it's not relevant to the viewpoint. So as stated, synthesis can cause artifacts and holes within the image. This is obvious in this example, where from a far point of view, this image looks fine. But as you zoom in closer into the finer details, you can see that there's a lot of data missing and edges and corners are not as well defined. So to solve this problem, they propose a refinement network. This refinement network is almost exactly like the refinement network used in the DeepMVS structure. It's akin to denoising. So what they do is they take a pixel from the novel viewpoint and extract a 64 by 64 patch around it. The amount of patches needed for this refinement network is arbitrary, and the reason they did this is because for some viewpoints it can be obvious what patches are necessary, but for other viewpoints the patches may be occluded or missing. So they needed a network that could take a varying input. And they select these patches using an educated selection based on the discontinuities within the disparity maps. So for areas of discontinuity, there's going to be artifacts because the network doesn't exactly know what's going on there. So to solve this, they look at where that discontinuity is, and they look for different viewpoints facing that discontinuity. And given the other viewpoints, there's most likely going to be a viewpoint that doesn't have discontinuities or clearly shows the object. So what they do is they take the patch from this novel view, they encode it, and then they also take the patches that are supplemented into the network and they encode these values and max pool them. These layers are then, or these max pooled values are then encoded into the final, or concatenated into the decoding process, allowing for a final decoded patch shown here as the novel view. And as you can see, some of these patches have objects that others don't. So for instance, in this viewpoint, you can see a car and the pole, but in other viewpoints, you might not see the pole, and you might only see the car. So things like that are useful for the refinement part. Same thing with this pole. You can see the pole, but not the car. It's a matter of just picking different objects within the view and pooling those features. So in order to get these patches as close to as possible, they have to warp the patches. And warping is based on the homography induced by the plane at disparity D. And what that means is they essentially look at the homography between the source image and the novel viewpoint. They look at the planar space, so just a slice of the image, and look at different views at that image and calculate an affine transformation. So they use this function here, which all this does is takes a patch Pij, and based on the homography at a certain depth value, it applies the warp necessary to get the same point of view. So to train this refinement network, they use a perceptual loss. The perceptual loss comes from the paper Perceptual Losses for Real-Time Style Transfer and Super Resolution by Johnson et al. This paper proposes two different losses, but one is for feature reconstruction and one is for style reconstruction. For this purpose, they only care about feature reconstruction. So this loss function can be seen as a feature matching loss, where they encode a bunch of features from various levels of of the 2D convolutional base network, usually VGG, and they just look for the loss between them by doing almost like an L2 loss, but it's averaged based on the shape of the feature map. So here the phi sub j represents the activation at this j layer, where this y represents the proposed feature, and then here is the ground truth feature. This is then just squared and normalized and then divided by the feature map shape to give an average for each pixel. So using the previous example, we can now see that once this image is run through the refinement network, you take patches like this, which were once blurry, and are now much clearer and have clear corners, not missing artifacts, and overall just much better quality. So the problem with this paper is they only use one data set. They only use the MVS synth data set, which is proposed in the DeepMVS paper. This data set is 120 sequences of images from the game GTA 5. The reason they use this game is because they can get all the information about lighting, camera parameters, depth, volumes. They can get everything they need to have a proper ground truth. Each sequence has 100 frames in it, and the images themselves are of an urban setting, meaning that they kind of look like a real world. Even though they are synthesized, they do represent real world images. So this allows the network to generalize for even real world examples, as you'll see later on. So to evaluate the network, they do all their quantitative results using the MVS synth dataset, and they compare that to the stereo magnification paper. The reason they do that is, although stereo magnification is a different problem, it can be seen as a view synthesis problem, because magnifying an image is similar to just creating a viewpoint closer to the scene. So the two evaluation methods they use are structural similarity index and peak signal to noise ratio, or SSIM and PSNR. They're a measure of quality loss due to encoding. And for the rest of the results, they use qualitative results on real images. They don't give a standard of measurement, but you can see visually that they are better images. So for the results, as you can see, the warped images, which are pre-refinement, they do slightly better in terms of SSIM compared to the stereo magnification paper, but they are noisy, which was shown by the artifacts and the holes within the images. So once these images are refined, you can see that the quality goes up higher with a higher SSIM value and a higher PSNR value. And the problem with this network is you take a deep network just to create the depth maps, then you pixel independently synthesize the image, and then you use a refinement network, and this takes a lot of time. So based on averages, given the two inputs as the network input, the depth probability volumes take on average 40 seconds to calculate, the view synthesis takes 30 seconds to calculate, and the refinement takes 28 seconds. So here are some comparisons between the stereo magnification paper and the extreme view synthesis. From a distance, both these images look relatively similar, but when you zoom in, you notice that the stereo magnification paper struggles to define sharp corners and really to determine what something in the foreground is compared to the background. The stereo magnification paper advertises that they can get 4.5 times magnification, whereas the extreme view synthesis can get up to 30 times magnification. And this is very clear here with a zoom in of the face. You can see that this statue is almost entirely clear with very defined edges and overall just a better quality. Same thing in this picture where you can see the bikes and the textures are very blurry within this image, but using the extreme view synthesis network, they're able to get much clearer images with sharp corners. So one last comparison they do is to Soft3D. Soft3D is a network proposed by Penner et al. That tries to tackle the same problem, but focuses more on texture sampling and finding better quality samples for refinement for the actual textures. So as you can see, the difference between the overall structure is relatively unnoticeable, but when you look at the plants down here, this paper does a much better job at cleaning up these textures, while as the extreme view synthesis gets the general idea, but for small textures like that, it struggles. So the limitations of this network are that the refinement network does not hallucinate pixels. All it does is looks at patches from different viewpoints and finds similarities between them and refines the actual image based on that. As stated in the presentation on Tuesday, there are GAN-based approaches to better hallucinate these pixels, but that in itself defines new problems like having to define what objects are potentially in the scene, whereas this paper can be applied to any real-world scenario. In addition, the novel views are affected by depth quantization artifacts, meaning that it can be difficult to define what the depth values are along edges, and this creates artifacts. So to conclude this network and architecture is heavily influenced on the DeepMVS. You could even argue that the whole paper is essentially DeepMVS just restructured, because the actual depth probabilities come from the DeepMVS network, and the refinement is also used within the DeepMVS network. So it's essentially just rearranging the network to get better views. The only difference being is they actually synthesize the images in this paper. In addition, they show that they're able to synthesize images with clarity with as little as 2 images and from varying viewpoints. One problem is that this paper struggles in the results section. They give very little information compared to other data sets. If you look in the DeepMVS paper, they used a lot of other data sets and a lot of other measuring metrics. So I don't know why they didn't try to apply those same data sets and kind of see what the results were in comparison. And the last thing is that this code is publicly available. Penner and Zhang with the Soft3D network are able to get better results for textures, but their code is unavailable, whereas this code is publicly available.